everyone, my name is Victoria Amyaga, and I did my extended essay on maths, more specifically an exploration of the coin rotation paradox. The idea for this essay came from a viral YouTube video called The SAT Question That Everyone Got Wrong. Me and 13 million other people watched this video, and said SAT question is this one. The radius of circle A is a third of the radius of circle B. Circle A rolls around circle B one trip back to its starting point. How many times will circle A revolve in total? And then the answers. Right, for some context, the SAT is a standardized exam for students our age to apply to university that tests math and English. The math questions are only supposed to take around a minute. So really it should be a very simple math question. This is one from 1982, and a student would be expected to solve it, probably something as follows. The circumference of a circle we know is 2 pi r. We can name the radius of circle A to be x, the radius of circle B to be 3x, right, to show the radius, the ratio between their radiuses. And then we can find the ratio between the two circumferences, and we'd get an answer of 3. And one would assume that this means that circle A would have to revolve 3 times in order to complete one full revolution around circle B. Right, so the correct option from the SAT question would be B. However, it was not B. And neither was it A, neither was it C, D, or E, because the SAT test question writers wrote their own question wrong. They solved the question wrong because the correct answer was 4. So how could such a simple 1-minute math question have such a counterintuitive answer? So the video goes on to explain that it is a version of the coin rotation paradox. The coin rotation paradox is when you take 2 coins that have an equal circumference and you start revolving one around the other. Despite the 2 having an equal circumference, the rolling coin would have to make 2 revolutions rather than 1 to complete a full trip. So you can see as follows. It starts rolling, it makes 1 revolution, then it continues to roll, and it makes a second revolution, right, despite them having the same circumference once again. So the SAT question explained exactly this, and then starts describing why this happens, right? In the video, it's a very good quality video, very interesting. I highly recommend you watch it. I enjoyed my 15 minutes of my life. And it goes on to explain a very simple, very visual explanation. I'm sitting there and I'm going, yes, this makes so much sense. This is such a cool problem. And then the video ends and I realize I understood nothing. It was so simple that I understood everything that video was saying, but it didn't explain to me what was this movement, why did it need an extra revolution, right? It simply showed it. So from here, my research question was born: how can the solution to the coin rotation paradox be mathematically proven? Right, so everything up until now is something of what my introduction to the essay looks like, and now we can move on to the case study, which is the mathematical body of my work. So my approach consisted of looking at the movement, and I chose to monitor a point on the circumference of circle A and monitor it as it goes around circle B. Right, so as circle A begins to revolve, and circle A is the circle revolving. Just to clarify the way the SAT question is, for the rest of the essay I refer to circle A as the revolving circle, and circle B is the one that's stationary. I also began with the classic coin rotation paradox, where the radius are equal, in order to explore that first, and I equated both radiuses to 1 in order to make my calculations a little bit simpler to look at. So from there, circle A begins to revolve, and if we track the circumference, the point on its circumference, we get a shape that looks something like this. This shape is called a cardioid. Fun fact, a cardioid it means heart, because it looks a little bit like a heart, no? And then I did this diagram. This is the one in my actual essay. I drew it by hand. I did all my diagrams by hand in order to have them match my essay. And this is what I'm showing, this cardioid. And then I did a little bit of math, and I did a little bit more of some math in order to find the length of this red dotted line, and I got that it's equal to 16. And I go, 16? It makes no sense. I was looking for 2 revolutions, right? So I look at the 16, and for a very long time, I kept trying to divide it or manipulate it in ways to get those 2 revolutions, and it just didn't make any sense, right? And then I realized I was wasting my time because I was doing the wrong thing this whole time. A point on the circumference of circle A, it has a very interesting pathway, but its velocity is very much dependent on the orientation of circle A. So it's not a linear pathway, it's going in this weird shape, right? But circle A, as the circle altogether, it has a constant velocity. It's moving at 1 speed around circle B. So it simply makes no sense to calculate it based on a point that has a pathway that's very different to the movement of circle A, right? So I looked at the movements again, and I realized I should look at the center of circle A instead, because that's the only point on circle A that has this constant velocity that is representative of the movement as a whole. And so I repeated the same maths once again, but this time I was finding the length of the red dotted line, which is now the pathway followed by the center of circle A, and I found that this pathway is equal to 4 pi, which makes a lot more sense. And because the circumference of circle A is 2 pi, and the ratio between 4 pi and 2 pi is 2, which is precisely those 2 revolutions. So from there, I decided to, okay, so we've done it for the classic quantitation paradox. Now let's look at the SAT problem where the ratios between the 2 circles was different. So to prove this one, I grabbed a pair of scissors, cut out 2 circles out of paper, and I used a ruler to find a ratio between the 2 radii to match that of the SAT question. So I labeled one as x, which is the smaller circle, and then the larger circle has 3x, just like in the problem. And I physically took them and I rolled it around, and I was able to confirm that yes, in fact, there are 4 revolutions. So we've shown that the paradox works for 2 circles with the same radius. We've seen that it works physically for 2 circles with a radius ratio of 1 to 3. So I went on to use mathematical induction, which is a formal method of proof, just to show that it is in fact a paradox that is applicable to all circles. And the conclusion that I came to is yes, in fact, this rule works despite any ratio of the circles. So it's not just 1 to 1, not just 1 to 3, but any 2 circles you have, they are going to have this one additional revolution. Right? So we found this revolution, we know where it comes from, but why is it there, right? I wanted to go deeper and see further, and I realized something. If we were to replace circle B with a square, right, it's also a regular polygon, but the difference is it has very clear external angles. Right? We know that an external angle of a square is equal to 90 degrees, and 4 external angles of a square, each by 90, that means there's 360 degrees worth of external angles that circle A must cover in order to complete its path. And 360 degrees is precisely where that one revolution comes from. A circle is also a regular polygon. The only difference is that it has an infinitely large number of infinitely small external angles, right? So though we can't calculate one single angle, we know that their sum must equal to 360 degrees because that is the nature of a regular polygon. So that's where that one revolution extra comes from, is because it must be there in order to account for the external angles of the curvature that it is rolling on. And just to prove this once again, I came back to my physical model, and I took a piece of yarn and I wrapped it around a larger circle, and then I spread out that yarn into a linear pathway, right? So it's still the same length as the circumference, but there's no external angle to cover. And in that case, when I rolled the little circle around that linear equivalent of the circumference of circle B, I got that it only needed 3 revolutions. So it is in fact shown here that that one additional revolution is because of the shape that is rolling around, the external angles that it's covering. So I was done with this part of my mathematical body, and then I thought, okay, can I give meaning to this somehow more? I'm really trying to show you guys the pathway and my train of thought that I was going through in writing this essay. And I thought, okay, I need to give this some meaning, need to give it some real-world application, and I realized that the quantitation paradox is very crucial in the basis of astronomy, specifically in sidereal timekeeping. So I made a second part of my case study, which is the application of this mathematics to astronomy. So sidereal time is the measure of time by tracking the Earth's movement relative to distant stars. What this means is that we usually use solar time, right? We know that there's 365 solar days in a year, there's 24 hours in a day, so on, right? And so if you can see on the diagram, this is once again the diagram used in my essay, when we base on solar time, we base it on the sun, right? So if I'm standing on the equator today, tomorrow at the exact same time, the sun will once again be directly above my head, right? But this is not true to 360 degrees exactly, because while we're revolving as the Earth, we're also in orbit, which means that in order to face the sun exactly, we must revolve 361 degrees a day, or approximately that, as you can see in the diagram, right? And for sidereal time, it ignores that one extra degree, and it does precisely 360 degrees. And this is very important for measuring stars and celestial bodies, because while we're revolving around the sun, those celestial bodies are not. So in order to keep track of them, we must base it on sidereal time, which is precisely 360 degrees. So sidereal time systems, they have the exact same thing. In a sidereal time year, you have 366 days. Exactly like in the quantitation paradox, you have that one extra revolution that is needed to account for those external angles that otherwise in a solar year are accounted for daily by 1 degree. So they're used to track celestial bodies in space. There is a similar idea of longitude and latitude like we use on the globe, but for space, which is for ascension and declination, and they're measured in sidereal time units, right? And this is precisely why we think that stars are moving in the night sky, because the stars are not moving, but we are rotating more than 360 degrees. We're rotating slightly more. So every day, the stars in the sky are shifting by 1 degree. Because every single night, we're not exactly where we were in terms of degrees as we were before, right? So this means that without sidereal time systems, we would have an awfully hard time tracking these stars in the sky, because every single night they're in a new place. But with sidereal time, they're going to be in the same place every single time, right? So this quantitation paradox, the understanding of it is incredibly crucial in order to have this concept of sidereal time and advance our knowledge of astronomy. So the conclusions that I came through with my essay are that the coordination paradox is correctly calculated by finding the ratio between circle A's circumference and the pathway its center follows, rather than the circumference of circle B, right? That's the very first thing we established. Finding the pathway of a point on circle A's circumference, the shape of a cardioid, what I was saying, is not valuable because the velocity at this point is constantly changing, and thus it is not representative of the circle's movement as a whole. The additional revolution is needed to account for external angles of circle B that circle A must cover. The paradox is relevant beyond theoretical maths, especially in the basis of astronomy, and paradoxical maths has practical applications in this case, without which we could not be able to track the location of objects in space. Right, so through all this, I came to the conclusion that by answering my research question, I've been able to show that it has been possible to show the interconnectedness of science with mathematics, that a seemingly very simple math question that should only take a minute is not so simple when it comes to actually defining it, and is much less simple when it comes to its real-world applications. And though mistakes are of course part of human nature, stuff like this needs to be very monitored and very understood mathematically in order to avoid misunderstandings on a greater scale. And that's the end of my presentation. Thank you.